Alright everyone, so now what we're going to do today is a bit of a shorter video, and it's going to be on kind of applications of derivatives. So some somewhat practical examples of the techniques that we've been developing so far. Okay, so the two major things that we want to remember are what we've said about rates of change. So one, we said we have the average rate of change over, typically in this case, some time interval, t1 to t2. So that is just the rise over the run. So the change in the f values divided by the size of the interval. So if you have the time interval t1 to t2, your average rate of change is going to be f of t2 minus f of t1 all over t2 minus t1. And then our instantaneous rate of change was the limit as the time interval goes to 0. So your f of a plus delta t, so the change in time, minus f of a all divided by the change in time. So the first thing that we can talk about is some physical applications of dealing with velocity and then also acceleration. So the velocity is just the change in position with time, and then the acceleration is just the second derivative of position or the change in velocity with time. And if you're in physics, you may have done higher order ones. So the next one, so the change in acceleration with time is the jerk. And then after that, you unironically get Rice Krispies showing up. So the next ones are snap, crackle, and pop. Okay, so let's suppose that we have some object is moving along, we'll imagine it's the real number line. So we have a positive direction, we have a negative direction. So we'll say that the positive direction is to the right, the negative direction is to the left. If the object has a positive velocity, that means it's moving to the right, so moving in the positive direction. The reason for that is if the change in position is positive, it's gone positive distance over your time interval. It's the simplest way to put it. If your object Okay, so if at some point the velocity is positive, that says that instantaneously that your object is going to be moving to the right, so moving in the positive direction. If you have a point where the velocity is 0, that means it's neither moving to the left nor to the right at that instant. So it's at that time instant, it's constant, it's at rest. So one place you could think about this that we've kind of seen already is if you threw a ball up into the air, it would be moving up and then it would start to come back down towards you. And in the instant where it's changing from moving up to moving down, that instant is going to be where the object is at rest. Okay, and then anywhere where the velocity is negative, that tells you that the object would be moving in the negative direction. So as we've conceptualized it, moving to the left. For acceleration, we can talk about when an object is speeding up and slowing down. So if the velocity and the acceleration are going in the same direction, then our object is speeding up. So if the velocity is positive and the acceleration is positive, that means the object is moving to the right, and the acceleration being positive says that the velocity is going to increase. So it's going to move more to the right. If you have something where the velocity and acceleration have different signs, then that says your object is going to be slowing down. So if your velocity was positive, that would say you're moving to the right, but if the velocity is negative, that says you can think about it as it's kind of pulling back your object. So it's making your object want to move to the left even as it moves to the right. It's maybe a confusing way of saying it, but we can look at some pictures and kind of see what's going on. Okay, so here I have a red curve, which is position, a blue curve, which is velocity, and a black curve, which is acceleration. So what we see is that the object starts out at the origin and it starts moving in the positive direction. And as it's moving in the positive direction, we see that the derivative curve, so the velocity, is always positive. Okay, and then what we see is that as our object, or as t gets closer and closer to 2, the object is moving slower and slower. And what the reason for that is because our velocity is positive, but our acceleration is negative. Now, after we hit t equals 2, velocity and acceleration are negative, and what we see is that the object is moving faster and faster until we hit about time 4. So we could think about moving faster and faster as the slopes of the tangent lines are getting more negative in this case. And then once we hit t equals 4, the acceleration curve becomes positive. So once it becomes positive and the velocity is still negative, our object starts to slow down. Okay, so then once we hit time 6, the velocity is positive again, and the acceleration is still positive, and what we see is that the object increasingly is speeding up as time goes on past time 6. Okay, so then we could go and look at a temperature function, and we could go and ask, in this case, how fast is the temperature rising or falling? So how fast is the temperature changing at some various points? Here what we'd have is that our temperature is given by a third t cubed minus 3t squared plus 8t plus 10, and t is being measured in hours after noon. Okay, so the first question that we have is how fast is the temperature rising or falling at 1 p.m., so at t equals 1. At t equals 1, we would have t prime is t squared minus 6t plus 8. T prime of 1, we're then going to insert 1 into these expressions, and we'll get 1 squared minus 6 plus 8, so 3. Okay, so in our next one, we have, we want to find how fast our temperature is rising or falling at 3 p.m., so finding this for t equals 3. Here what we're going to have is the same kind of derivative, just we're now going to evaluate it at t equals 3. And when we do that, we get 3 squared minus 6 times 3 plus 8, which is minus 1. So what it says is that our temperature is falling at a rate of 1 degree per hour. And then the second question that we had is, or I guess the third question, when is our temperature stationary? So when is the temperature not changing? In this case, we would say that the temperature is not changing when t prime is 0. And when is t prime going to be 0? Well, t prime is 0 at t equals 2 and t equals 4. So those two are going to follow directly from just factoring the derivative and seeing what you wind up with effectively. Okay, so the next example that we have is a function r, which is measuring blood pressure based on the dosage of some drug. So our dosage is measured in milligrams, and our pressure is measured in milligrams of mercury. So standard units of pressure. Okay, so for us, we have this given function r, and where we need to take the derivatives, I'm just going to give you the derivatives and go from there because they're we could find it using the chain rule and stuff, but it's not the most informative example, so we'll just take it as given. Okay, so what we want to do is we want to determine the sensitivity to for this function r in terms of dosage levels. And the sensitivity is going to be looking at the derivative. So in other words, we're going to be saying, is our derivative going to be positive or negative and such. And what the sensitivity is going to measure is the impact of increasing the dosage level based on the reduction in blood pressure. And then the second question is going to be at which of the 3 dosage levels do we get the biggest bang for the buck effectively. Okay, so what we can see is that we can find our derivative it's given here. Again, we could find it using the chain rule from last time. And what we'd have is that at 5 milligrams, our derivative is going to be just under 1 millimeter of mercury per milligram of our dosage. Okay. When we increase the dosage level up to 15 milligrams, we get about 1.25 millimeters of mercury per milligram. So what that says is that we're getting a bigger reduction in uh, in blood pressure by increasing the dosage up to 15 milligrams. But then if we go on to 35 milligrams, what we see is that the rate at which we're going to decrease the blood pressure is going to drop down to about 1/3 of a millimeter of mercury per milligram. So we're getting a less impactful change. Okay. So we can go on and look at some production costs. So we can look at two different kinds of two different ways of measuring things. So one is the average cost and one is the marginal cost. So we're going to be given this cost function. If we want to, we could go and find the derivative for this function, which we could do simply from our power rule and our sum rule, and then we'll go and define the average cost as well as the marginal cost. Okay, so we are going to take the average cost to be given by this expression, the cost divided by x. So the cost of producing x tons divided by the number of tons. So if we find the average cost for producing 1,000 tons, we would find it's about $6.40 per ton, whereas if we produce 2,000 tons, we'll get $11.40 per ton. So in other words, the cost of producing more tonnage increases pretty substantially as we go along. Okay, and then the marginal cost is going to be equivalent. The other way you could say it is it's the cost of producing one more unit. So at 1,000, you're looking at a cost of $9.40, which is saying that after you've produced 1,000 tons, it'll cost you another $9.40 to produce the next one. So maybe depending upon what you can sell your, in this case, vibranium for, maybe you can sell it for more than $9.40, so it's worthwhile to produce the next ton. But once you produce 2,000 tons, it's going to cost you $25.40 to produce your next ton, which is probably not worthwhile. Okay, so no, second last example. Second last example that I want to do is on what's called elasticity. So the elasticity measures how your demand for a product is going to change as you increase the price. Okay, so elasticity is defined as the derivative of demand times the price, all divided by the demand. So for us, we're going to go find the elasticity, and we're also going to find where the demand is elastic, based on the demand function 286 minus 20p. Okay, so for the demand function is given, we could easily find that our derivative is minus 20, and then using the expression that we have for the elasticity, we'll go and find that the elasticity function is given by minus 20p, all divided by 286 minus 20p. Okay. So then what we want to do is we want to find where e is equal to minus 1. So we'll go and solve e equal to minus 1 for p, and when we do that, we get 286 equals 40p. In other words, our price point is going to be $7.15, where the demand is going to flip from being elastic to inelastic. And the last example I want to do is one dealing with gravitational force. So our gravitational force is given by F equals k over r squared. K is a constant. So the gravitational force is just a function in one variable. In this case, just the radius, so the distance that the two bodies are away from each other. Okay, so let's see. So what we're going to say is that when r is 4,000 kilometers, the gravitational force is going to decrease at a rate of 1 kilogram per kilometer. So as you increase the distance by a kilometer, by 1 more kilometer, the gravitational force between the two will drop by a rate of a kilogram per kilometer. So then we're going to ask is how fast does the gravitational force change when r goes out to 8,000 kilometers? Okay, well, this is dealing with rates of change, so we would expect a derivative to be useful in some way, shape, or form. To start, we're going to have that f prime is going to be minus 2k over r cubed. And we know that f prime of 4,000 is minus 1 kilogram per kilometer. And again, be careful of where the the minus sign in this case. So we get the minus sign showing up because the force is decreasing. Okay, so then what we want to know is what's going on when we get out to 8,000? Well, one way that we could try and approach this is try and solve for the k, but that's kind of inefficient. So what we're going to do is we're going to write out our expression for f prime of 8,000, and we're going to go and use what we know about f prime of 4,000. So at 8,000, we'd have f prime of 8,000 is minus 2k over 8,000 cubed. But we could rewrite 8,000 as 4,000 times 2. So 8,000 cubed is 4,000 cubed times 2 cubed. Well, then we could break this apart as minus 2k over 4,000 cubed times 1 over 2 cubed, which is 8. And we just set up above that minus 2k over 4,000 cubed is minus 1 kilogram per kilometer, so we'll go and take use of that. So we'll go and insert the minus 1 kilogram per kilometer in place of the minus 2k over 4,000 cubed, and that will tell us that f prime at 8,000 is minus 1/8 kilogram per kilometer. So when you're 8,000 kilometers away, the gravitational force between the two bodies is quite small, and also decreasing at a pretty small rate. Okay, so that goes and gives us kind of a broad enough idea of some ways in which derivatives show up in various environments, and there will be a worksheet sitting in while courses over these topics. Okay, and I will see you all in the next video.